So good morning and thank you for attending the session. The session probably is only going to take 60 minutes and the topic of the session is network tuning in AIX. And what I've done is I've taken together some basic network tuning tips and also I've added some slides on 10 gigabit networking as well as some debugging tips at the end. There was an article that I published earlier this year in January on network tuning, and that article I've provided the link here at IBM Systems Magazine. Hopefully you'll find that that's a useful article. It doesn't cover the 10 gigabit stuff that I'm going to talk about today, and I'll probably write an addendum to it to include all of that. So I'm going to start with a discussion on some of the tunables. So you'll hear people talk about tuning TCP receive space, TCP send space, RFC 1323, and also something called SB max. And a lot of people don't know what those are. So let's start out with TCP receive space. TCP receive space is basically the amount of data that the receiving system can buffer in the kernel. So you have a receiving sockets queue for TCP workloads, and this is the amount of space that we're actually going to reserve for those workloads. The TCP send space tunable specifies how much we can buffer before we send it out. So it's important to get those right because it affects your sending and receiving of TCP workloads only. There is a separate tunable for UDP, and there's actually a different queue for IP workloads. By default, those are set to 16K each, and that is typically too small. They are also impacted by something called RFC 1323, which is also known as the window scaling option for TCP, and sometimes you'll hear it referred to with respect to something called the Nagel effect. Basically, TCP has a 16-bit limit for window sizes, which means that the maximum buffer size is 65,536. You can make TCP receive and TCP send as big as you want, but if you don't change RFC 1323, you are still limited to 65,536. So I quite often see things where somebody has set TCP send and receive to like 262.144, but they have not changed RFC 1323, which means they are still limited to 65536. So we change RFC 1323 to 1. This allows you to have much bigger windows, and the maximum size for that is going to be somewhere in the order of 4 gigabytes. So you're going to see when I give you the recommended tunables that we tune all 3 of these. Additionally, there is the SB max tunable, and that sets an upper limit on the number of socket buffers queued to an individual socket. Normally by default that is big enough and you don't have to tune it, but I have a recommendation that talks about making sure that it's at least a minimum size. So we'll talk about that one in a minute. We also have UDP send and receive, and a lot of people think there's no UDP traffic in their network. In fact, there's significant UDP traffic, if for no other reason than most people run DNS servers. So by default, UDP send is about 9K, and I think UDP receive is set to 40K, and that's typically not big enough. What we do with UDP send and receive is we set UDP send to 65,536. That is large enough to handle the biggest possible UDP packet that you could receive, and there is actually no advantage in setting it bigger. You should always just set that to 65536. Now UDP receive space is sort of interesting because it turns out you receive a lot more UDP traffic than you send, plus packets get broken up into certain sizes, so we have to set UDP receive space to significantly larger than UDP send. Right, this is the incoming data that we're going to queue on the UDP sockets, and once you hit that limit, then all the packets get discarded. So then you end up with stuff having to be retransmitted by the sender, and that affects your performance. So typically the recommendation for UDP receive is that it be set to 10 times whatever UDP send is, and then depending on how your performance is, you may bump it or make it smaller. I've almost never had to bump it. So this leads into the recommended starter set of tunables. And our recommended starter set of tunables is to use the no command with the -p to make it permanent to set these 5 parameters: the RFC 1323, TCP send, receive, and UDP send and receive. and you'll notice that there is a 0 on the end of UDP receive. I get emails all the time from people asking me if that's a typo. No, as I said in the previous slide, UDP receive really needs to be set to about 10 times of what UDP send is set to. I made the comment that there was no point in setting UDP send larger than 65536. It actually won't allow you to do so. That's because the IP protocol has an upper limit of 65536 bytes per packet. The other thing we need to do is check that SB max that I mentioned. Make sure it's at least 1040000. If it's at least that large, you're usually okay. By default, it is actually, I think, a little larger than that, but we'll check what that's set to. So I mentioned checking the actual interfaces. So if you run an ifconfig -a, you're going to see here that EN0, you can see TCP Send and Receive and RFC 1323, somebody hard-coded them on here. Now what happened is by default, IBM has started to, at certain TL levels, actually override whatever you have in the NO commands on the actual adapters. If we look at the service that I have, if you look here, hopefully this font is large enough, you can see that my TCP Send and Receive I actually overrode on the adapter. And that's because somehow they ended up, and I'm pretty sure it was the operating system did it at install time, they ended up being overridden, so I had to override them. And the way to override them is with the chdev command, which you see just here. So I did a chdev on EN0, set TCP receive, send an RFC 1323, and used the -P so that the changes came in at the next reboot. Unfortunately, when it's overridden on the actual adapter, you have two choices. You can stop inetd and disable the adapter, and then use chdev on it. That will happen immediately, and then you reactivate the adapter, or you use chdev on it with the -P and you reboot. Very few of us have the luxury of using inetd stopping it on a production server, but this is something you should check on your servers to make sure that, if you've gone and done the settings and everything else, you don't want to find that IBM has gone and overridden it. So typically, I'll do this ifconfig -a here, and then I'll do an no -a, and I'll grep the actual parameters. Now there is a parameter called useIsNo, and I'll just pull it up here. -a would help if I could type. All right, so that's actually become a restricted parameter, and I bring that up because useIsNo, what it says is whatever the interface is set to, that's what I'm going to use. If you set useIsNo to 0, it changes that, but they have now made it a restricted parameter. So your best option is to do what I just said, which is set the parameter using NO, and then do an ifconfig -a like I did here, and if you find that the values aren't what you set them to with NO, then you need to use chdev to reset them and then reboot. So another thing that I have here is that on my VIO servers, I also reset the transmit queues and the transmit queue size on my 1 gig adapters. And the reason that I do that is because they end up handling a lot of data, and you typically will start to see some issues with your network if you don't do that. So it's the actual underlying adapters. So as an example, this is my VIO server. EN6 is the actual SEA. The underlying adapters are ENT0 and I think ENT2. But if you look at ENT0, I haven't actually done it here, but here's my transmit queue size, and that normally I would bump. Just be aware that that's something that typically increase on the underlying adapters for your VIO servers. And this is just showing you my VIO server, which I just brought across anyway. But I always make sure, particularly on the VIOs on the SEA itself, that those settings are set. In the IBM manuals, you'll actually find that there is a page, I believe it's page 247, where they actually show you for each interface the speed, and with the MTU sizes what you should send TCP send and receive to. And pretty much anything that's gigabit and higher, you're going to set to these 262.144s. So I just use that as my standard. And I get asked all the time, well, why doesn't IBM just set the system to that automatically? The systems are basically set up by default to be generic Unix systems. So as an example, they're basically tuned for 100 meg networks, and we just don't run those anymore. So you really do, the one thing I can guarantee you is that your network is detuned if you haven't tuned it yourself. Another parameter that a lot of people aren't aware of is the ipqmaxlen. You don't have to change this very often, but it is the only tunable parameter for IP, and so we have TCP, we have UDP, and we have IP. And you'll usually hear it referred to as TCP IP as if they're one protocol. What this parameter does is it controls the length of the IP input queue. And what you're really looking for is if you run the netstat-p space IP, what you're looking for is interrupt queue overflows. I have seen them. It was a pretty busy network. I won't see them on the system that I have. You should be aware that it's something that you should be looking for. It's one of the things that I test for. And you'll see on my system here that when I do this netstat-p IP and I grep on IP interrupt queues, you'll see that there's no overflows. But if you see numbers in there, then the next thing you're going to do is like an uptime. And I've been up for 14 days. If I had several thousand of these, I would probably get concerned and I would bump up my ipqmaxlen. And that's done again using the no command. Now, if you increase it, you want to be careful how you increase it, because let's say you made it 256. What that means is that the CPU is going to be spending more time in the off-level interrupt handler because now it's got a longer queue to deal with, so it's got to process more things through the sockets versus the packets getting dropped. So it really is a trade-off of reduced packet dropping versus CPU availability for other processing. So hopefully that's all making sense to you. So these are some of the things you want to look at and make sure they're set. I said I would talk a little bit about 10 gig Ethernet adapters. There's a lot of confusion out there, a lot of myths. Nigel's posted a lot of stuff, as has Gareth Coates, about some of the myths about 10 gig E, including things like that people assume that if they go from 1 gig E to 10 gig E, they're going to get 10 times the performance and so on. And while that is potentially possible, there are a lot of things that you have to do it right. So I'm going to talk about some of the things that I've picked up from Nigel and Gareth. So I'm going to start out with a little bit about the adapters themselves. There are a number of different adapters for 10 gig E, and there's one that I want to bring to your attention. A lot of people are looking at the 10 gig E SFP plus copper cards. So they do a form of, they call it copper twinax, but it's not twinax as you think of it when you think about coaxial cables. There are special cables that are required, and I will tell you, so that you don't have to learn the hard way, IBM only supports their own cables. There are 3 cables that can be ordered. They come in 1 meter, 3 meter, and 5 meter. And they're known as 10 gig E SFP plus active twinax cables. So just be aware that if you're looking at that card, there are specific cables that have to be ordered with it, and the maximum distance is 5 meters. There are other cables that work, but they aren't supported. Most of the people I know go with the 10 gig E SR cards, which are the fiber cards. It's just been in the last 6 months that people have started to do the SFP pluses, and I've started to run into this cable issue. So I just want to give you a heads up so that you don't get into that situation. And if you have any questions on it, feel free to email us and we'll give you some more details. The multifunction cards that go in a 770, there are 2 different ones. I've got the feature codes here because I think in feature codes. One of them is the copper SFP plus, and then there's the SR optical. So this is the fiber one. It has 2 10 gig opticals and 2 gigabit copper Ethernets. So it's actually a combination card. But it is important that you talk to your network people and understand which kind of 10 gig E they want you to do. Okay, so let's talk a little about network performance and throughput and how 10 gig E can affect that. This is motherhood and apple pie, but network performance and throughput depends on a number of different things. CPU power, because some things like assembling and disassembly can be handled by the CPU. Some things are handled with TCP offload on the adapters. It varies. The MTU size has a big impact. If you have the default MTU size of 1500, then you're probably going to do very little packet assembly disassembly. However, using jumbo frames, which is an MTU size of 9000, will significantly improve performance provided everything between the sender and receiver is set to that same MTU size. So anytime you want to change MTU size, you need to have a discussion with the network people. Otherwise, you can actually make performance worse, because if I send an MTU size of 9000 and you're breaking the packets into 512 bytes at all the routers, that's going to cause quite a few issues. The distance between the receiver and sender is important. You run into latency there. It also depends how it gets there. Is it getting there via straight cables? Is it getting there over wireless? Is it getting there through satellites? There's a number of things that affect the latency. Then there's all the offloading, coalescence, and aggregation features. You know, how much of it's being handled by the card versus the CPU, that's the offloading. And coalescing and aggregation just refers to how it's actually going to combine things and send them out. There's your configuration. There's your firmware. Particularly with 10 gig E cards, you need to keep your firmware for the adapters and the server up to date. There have been a number of fixes for performance issues for 10 gig E, and then the same applies for the E fixes for 10 gig E. Those are pretty well published, what those are, but there are a number of fixes out there for 10 gig E performance. So you need to make sure that you're on board with all of those. And it's more so than gigabit E that you have to do that, because these adapters are just handling so much more bandwidth. Some of the notes that I picked up from Nigel and Gareth, they highly recommend switching to jumbo frames because it lets you use the full bandwidth of the adapter. With that said, you still need to coordinate with the network team. Jumbo frames is an MTU size of 9000, and that cuts down on the CPU time needed to forward packets if they're larger than 1500 bytes, which many of them are. So if all your packets are small packets and they're less than 1500 bytes, you get absolutely no benefit from an MTU size of 9000. So you need to know the size of your data. As an example, I actually used to use an MTU size of 9000 on a system we had that did voicemail and that moved large mail messages between servers. And it was a significantly better performance moving to the MTU size of 9000, but it was one of those things where it never really left the box. So we didn't have to deal with any of the network routers or anything like that. When you go to an MTU size of 9000 or jumbo frames, you have to do it end-to-end. So the virtual Ethernet, the shared Ethernet adapters, the Ether channels, physical adapters, switches, core switches, routers, etc., you need to check that those are all set the same way, assuming that you're using them. Otherwise, you're going to find they fragment your packets. So one place that I see jumbo frames used a lot is when there's two LPARs on the same box talking to each other, because then you just have to set it on the virtual Ethernet, and the performance improvement can be as much as 3x, but on top of that, it also takes less CPU. They did some tests where for virtual Ethernet, two LPARs talking to each other, the CPU needed to handle the networking was halved when you went to jumbo frames. Now that has nothing to do with 10 gig E, but it's an important thing to note for virtual Ethernet, particularly since we talk virtual Ethernet between the LPARs and the VIO server that's handling the SEAs. This was a big bugbear, managing the expectations. Going from gig E to 10 gig E does not mean 10x performance. You're going to need new cables. There are special cables that you use for 10 gig E, even if you go with the SFP plus copper. You will use more CPU and memory. That's because all your network traffic gets buffered. Those buffers get handled by CPU and they live in memory. And this in particular applies to the SEA and the VIO server. If you're doing 10 gig E direct into an LPAR, you still have to think about this. You also need to make sure that your switch can handle it if all of the ports on the adapter get connected and they all run at 10 gig. And you need to make sure that the server has enough CPU to actually deliver the data to the network at 10 gig, because 10 gig does put some overhead on the server. And there are actually also memory calculations for overhead for 10 gig adapters for the servers. So some additional tips: you need to turn on flow control everywhere. You need to turn on the network switch, you need to turn on the adapter and the server. You're never ever going to get the bandwidth of a 10 gig E without flow control. And flow control is going to stop the 10 gig E flooding everything, which reduces the need for retransmissions. If you really need significant bandwidth, you may want to consider dedicating the adapter to an LPAR. You can still make things like LPM work by using scripts to temporarily remove the adapters, but you may want to consider that if you've got an LPAR where you really want to take advantage of the full bandwidth and you don't want to compete with anyone. You also want to look at two very critical TCP offload settings, large send and large receive. And yes, large send is one word and large receive has an underscore between large and receive. I have no idea why they spelled them differently, but they did it. Large send is also called TCP segmentation offload, and this should be enabled by default on a 10 gig SR adapter, but it's something that you should still check. And the way that, if it's not set, the way you change it is with this chdev command with large send equals on, or in the VIO server, you use the chdev-dev. And it's large send equals 1 there. The other one is large receive. And large receive is what we call TCP segment aggregation. And again, that's something that you want to set on. The combination of these is going to improve the throughput through the TCP stack significantly, and it will really help with performance. And the nice thing about the SEA is that if you set large receive on the SEA, all of the LPARs the client LPARs will actually inherit that setting. However, you'll still need to set large send. We talked about the MTU size. Sometimes people go significantly above the 9,000 and they use 65535. That actually reduces traffic and CPU overhead, but still gets you the bandwidth. And another thing to note, the reason that we use chdev rather than ifconfig to make these changes is because chdev updates the ODM. ifconfig does not, so that when you make the change, it doesn't survive a reboot. So you really want to use chdev. Okay, something a lot of people don't understand as well is that network performance is affected by CPU entitlement and VPs. Those packets use CPU to get built. So we need to make sure that there's enough CPU entitlement or virtual processors at the VIO server if you're using SEAs and in the LPAR if you're not, in order to build that. There's a program called netperf and another one called ipqmaxlen. You can actually use those to do network bandwidth testing. There is actually a limit to the virtual Ethernet speed, and it's somewhere between about 0.5 to 1.5 gigabits per second on the backbone. In terms of where two LPARs are on the SEA, where one is on the SEA and the other is external, the speed between them is going to be the lower of the virtual Ethernet speed or the speed of the physical network. So whichever one is lower is what you're going to get. Versus when they're on the SEA and they're on the same box, it's going to be limited to the virtual Ethernet speed. However, also keep in mind that every virtual machine or LPAR on the server could be sending and receiving at the virtual Ethernet speed concurrently. So while it's, let's say it's 0.5 gigabit per second, if I've got 10 LPARs sending at that is possible. And Gareth has a very nice webinar here on PowerVM 10 gigabit Ethernet. I highly recommend that you download it and listen to it. It's very, very good. I found a very good document by Nathan Flowers called Performance Issues with 10 gig Ethernet. What he was really trying to show was that the idea of flow control is that it's going to prevent buffers from being depleted. The problem is that just like any kind of performance tuning, it's a moving target. So in this case, we might fix it in one place and then we move it to the next place that's throttling traffic. So the example here is showing that the server and the switch and the core are all great. They can handle 10 gig, no problem. You know, the real issue is all these guys can talk 10 gig, but this little PC client can't. So the idea of flow control is to try to make sure that the client doesn't get overrun, but you may need to have it all the way through here in order to make sure that while these guys can speak at this speed, they don't try to overrun this guy. This is a very good paper that you should be able to Google to find. So this is from Alexander Paul's presentation, and he kind of shows all the different areas that you have to think about. So here's my client LPAR. It's talking virtual Ethernet through the virtual switch and the hypervisor to the VIO server, which then, of course, is really an SEA. That SEA is made up of an Ether channel of two 10 gig ports. It goes out for the 10 gig E network, which has routers and switches, etc., and then comes in at the other end and goes through to another LPAR. So if you look at this, you can actually see that there are multiple points. There's a virtual Ethernet here, a virtual switch, a virtual Ethernet. All of these, if you're doing things like changing MTUs, you need to check each one of those. A couple of things that Alexander pointed out was a lot of people use FTP to test the performance and throughput, but it's actually single-threaded. So the problem with using something that's single-threaded is there's a limit on the throughput that one thing can push. If you decide that you're going to use FTP, you need to run a whole bunch of FTPs at exactly the same time in order to really be able to push the 10 gig. It's actually better to use ipperf, which you can download, and that actually allows you to test bandwidth. It's multi-threaded. You can do TCP benchmarks. You can do UDP benchmarks. And basically you set up a client and a server, and then you tell it to run for 60 seconds and use 8 cores and, have a nice time. There is a GUI Java front end called jperf. I've never actually used it, but it supposedly lets you change a lot of the settings. Alternatively, you can use netperf, which I mentioned earlier, and this has 2 benchmarks built into it. One is TCP stream, the other is TCP RR. What I do recommend you do is that once you think you've got your 10 gig network set up correctly, I would recommend that you go and grab one or both of these and just run some tests and see what throughput you're really getting. And from there you may be able to figure out where you're actually running into issues. That's what I have on 10 gig E, and now we're going to look at some slides on actually looking at performance and how to debug it. So first, there's a bunch of different network commands. There's netstat or entstat. You can run either of those. There's netpmon. Now netpmon goes and gathers a bunch of different statistics, but it does run a trace in the background, and so it can add some overhead on the server. The same with iptrace. TCP dump is an excellent tool because it grabs every packet. However, it turns your Ethernet adapter into promiscuous mode, which if you're running any kind of IDS on the network is going to throw a very big red flag. So normally what I recommend to people, if you think you have to run TCP dump, I would go and talk to the network and security people and make sure they're aware of what you're doing and why you're doing it. That way they don't come pounding up to your desk and get mad at you. A trace route is used for tracing the paths that the network follows in order to get to your remote location. Chdev and Alice Adder they use for changing and checking. NO is used for setting the actual settings for the network. ifconfig we saw, and then we talked about netperf and ipperf. Ping, I don't normally use to test the network. I normally use it just to test if something's there. And I mentioned you can use FTP to measure the throughput, but just remember that it's single-threaded. So if you're going to do it, you need to do a bunch of them. So normally I would write a script that does 7 or 8 of them at the same time. And what you should be expecting, so for gigabit, at best case you're going to get 948 megabits per second of simplex. And you'll be lucky to get that really because most of these protocols are very chatty. And that's the thing that people forget is, they see they have a 10 gig network, and even if you do everything perfectly, you're probably not going to get 10 gig. And the reason is because TCP sends packets and then it waits for responses. It's very, very chatty. It sends data, it waits for an ACK. And there are actually tunables that affect how quickly those ACKs come back. If I look in nmon, and I look in the nmon analyzer, you can see the net tab. And in the net tab, what it's going to tell me is kilobytes, not kilobits, kilobytes per second for reads and writes on my Ethernet adapters. So here you can see I maxed out at about 11,000 kilobytes per second on EN0 for reads and 16,000 for writes. And then you can see that the actual average is more like 4,000 and 6,000. So that can give you an idea of your actual throughput. There's not really anything else to say about that. Now, if we look at some other network things, if you run a netstat-v, you're going to find that you're going to be looking for overflows and memory allocation failures. You'll see a couple of parameters in there, and one of them is the maximum packets on the software transmit queue. The other one is software transmit queue overflows. You also may see packets drop due to memory allocation failure. These are packets that have had problems and have actually ended up not being able to be transmitted. So for instance here, the software transmit queue overflow. Since this machine came up, 9,522 packets were not able to get into the queue because the queue was full. And the maximum packets at a time that were on that queue were 884. When you start to see these, that's when you start to look at increasing that adapter transmit queue. Now, if you remember, I said that I actually do it automatically, particularly on SEAs. And the reason I do that is because I like to avoid these things. You're also going to look for receive errors and transmit errors, DMA overruns, and DMA underruns. So if we look at a netstat on my EN0 on my server, it's going to give you my hardware address. It's going to give me my uptime, which is nice. So I've been up for 1 day and 20 hours and 37 minutes. Here's my transmit and receive statistics. And here's my max packets on the transmit queue and my software transmit queue overflow. So I don't have any. Here's my receive errors, transmit errors, packets dropped. And here's my DMA overruns and DMA underruns. If you see things in here, and the thing you're most likely to see is software transmit queue overflows or packets dropped due to memory allocation failure. That's what I primarily see. That's when you're going to increase these adapter queues. There's also a parameter called TCP_no_delay ACK, and this is disabled by default. And I see this regularly in Oracle systems getting changed. So what happens is when TCP sends a packet, it waits for an ACK to come back. However, since there's a lot of traffic going to and fro, by default, what the receiver does is it waits 200 milliseconds or up to 200 milliseconds and then takes all the ACKs that it has to go back to you and it puts them on the end of the response packets and sends them then. So rather than every time it receives a request it sends an ACK, it basically coalesces them and it waits about 200 milliseconds. That means that your response is slightly slowed down but you have less traffic. What people regularly do on busy Oracle systems is that they will change that and they will enable TCP no delay ACK. So that what happens is as soon as TCP gets the data, it sends an acknowledgement. It adds a little overhead to the network, but it greatly improves performance. So your trade-off is more traffic on your network versus faster response. The nice thing about TCP no delay ACK is that it is a dynamic parameter. This is a parameter that I change all by itself, and you don't do this if your network's already overwhelmed. But if your network has plenty of available bandwidth, this is something you may want to consider, particularly on Oracle systems. And again, you just make the change, you monitor what's happening, and you change it back really fast if you have to. Another thing is that you can run an lparstat command, and what you're looking for is, do you have high virtual context switch rates? Because if you do, then that's an indication that your LPAR or VIO server doesn't have enough entitlements. So if you look at this server here, I know the server's doing nothing. My virtual context switch rates are, pretty low. If you see numbers that are much, much larger than that, then you're going to want to look at your entitlements and see what's going on with that. So if I was to do a vmstat 2 space 2, you can see I've got an entitlement to 1. I've got 4 LCPUs and I'm doing nothing. But just be aware that you can watch this PCSW and you can actually figure out, if you have enough entitlement. And as I said earlier, entitlement is really important for network performance. I talked about ipqmaxlen before, and this one you can run the netstat-s. I don't know if you've ever looked at a netstat-s, but I'll put one up. What netstat-s does is it takes each protocol and does a summary of it. So it does ICMP, etc., and then down here you'll see there's the IP parameters here, and the one that we're looking for is this one here, IP interrupt queue overflows. There is another flavor that you can do of netstat-s, which is netstat-ss. And what that does is it only gives you the ones that aren't 0. So it makes it a little easier to search through when you're looking for things that have been dropped or whatever. So again, in my IP, I don't see anything that's a concern for ipqmaxlen. And I mentioned before what the trade-off is. I also recommend, people forget, you really need to check your error report. There's nothing worse than reporting a problem and then somebody comes in, they run error report, and it says that there's a problem with your network adapter. And it's like, oh, kind of missed that. So always run ERRPT before you report something to IBM or anywhere else as a hardware problem. So let's have a look at a quick TCP analysis. If you do a netstat-p of TCP, it gives you a whole bunch more than this. But the things I'm looking for are comparing my to my packets retransmitted. All right, so this value here to this value here. And I want my retransmits to be less than 10 to 15% of my packets. If I'm retransmitting more than 10 to 15% of my packets, there's something wrong and I need to delve a lot deeper. The same applies with comparing packets received to completely duplicate packets. If I am getting lots and lots of duplicate packets, then there's something wrong, something's getting rerouted in a weird way. There's a number of things it could be. And in both cases, the problem could be a bottleneck on the receiver, or it could be too much traffic. So again, this is where you might want to look at what's your TCP send and receive space set to, and things like that. Another one to watch for is this discarded due to listener's queue full. That's typically an indication that the receiver is running out of queues. If you look at the IP stack and you look at the numbers there, what we're looking for is if we see like a lot of bad header checksums or fragments, particularly fragments drop due to dupe or out of space, that means that the network is corrupting packets, or the device driver receive queues are too small. So you need to go and look at the actual device drivers receive queues. If you see fragments that are dropped after timeout, and that's greater than 0, there's something called the ipfrag TTL, and that is the amount of time that an IP fragment will stay around waiting for all of the fragments of the datagram. Once that time comes up, it's going to drop those packets if all of the datagram hasn't arrived. And that can happen because the network's really, really busy, or you don't have enough mbuffs. By default in AIX, it sets mbuffs to half of memory, so we used to have to tune mbuffs. We really haven't had to for a very, very long time. But if you have a really busy network with a lot of congestion, it's possible that you could run into problems with the ipfrag TTL. You also want to look at the ratio of packets received to fragments received. And what you're looking for is what percentage of my packets are getting fragmented. So if I have a small MTU and more than 10% of my packets are getting fragmented, then somebody is passing some very large packets, and we're spending a lot of time assembling and disassembling packets. Something else to watch in the netstat-v is there's these things called tiny, medium, small, etc. buffers. And I bring this up because a lot of people aren't aware of them. If you see something in your netstat-v, and this is my shared Ethernet adapter, where it says packets dropped 286.155 here, and then I see number of resource errors, and the number's the same or pretty close, then we need to look at these things called tiny, small, medium, large, and huge buffers. So on my VIO server here, as I go down through my netstat, there's a section on my virtual I/O Ethernet adapter. And by the way, if you're using virtual Ethernet between two LPARs, you may see this as well. In my case here, I don't have any hypervisor send or receive failures or anything, but just imagine that I do. What we're really looking at is this section here with receive buffers, and you can see we've got tiny, small, medium, large, and huge. There's a minimum setting and a maximum setting and a maximum allocated setting. And what you're going to do is compare the maximum allocated to the maximum buffers. If they're coming close in allocations, then it's possible that you have a problem with the buffers and you need to bump them. That's what I'm going to show you on the next slide. This is a case on my VIO where we had a serious problem. You could see that there were, 67 million of them since boot. And when we went down into this virtual I/O Ethernet section, the hypervisor receive failures matched these numbers. Now they may not always match, but they may just be close. But just be aware of them, because most people are not aware of these tiny buffers. When I went and looked at the virtual trunk statistics that we were looking at before, down in that receive information section, I compared the maximum to the max allocated, and here I found that for my small buffers, my max allocated was the same as my maximum buffers. So I know that I ran out of those buffers, and the others were fine. What we then had to do was go back and change the virtual Ethernet, and I actually increased the maximum to 4096 for those small buffers, and I changed the minimum to 2048 so that I knew I would always have enough buffers. And you do it for the virtual Ethernet adapter that's configured for the SEA. Unfortunately, this does require a reboot, but a reboot is better than dropping a whole lot of network packets. So just be aware of that. Now, you can get a lot of network information out of nmon, and I happen to like these nmon settings here. What I found out that was new in nmon monitoring is that there's a capital O, and that gives you the SEA on the VIO server. You can actually get the same information in nmon interactively. So here I've got the capital O in my nmon. You can see my adapter, you can see the throughput, requests and size in kilobytes, etc. But what's really nice is when you're running nmon in logging mode now, you can actually add that -O, and it will get you that networking information. And getting information on the SEA, we used to have to run SEA stat to get it. Well, now we can actually get it here. You can also use topaz-E if you want to do it interactively. You can use ntstat and SEA stat, or you can use nmon-O. Additionally, if you are at VIOS 2.2.2 something or higher, you can use the VIOS Performance Advisor, and it will actually give you information and report on the SEAs as well. The couple of examples I have here is, this is an nmon that will run for 30 minutes and will take a snap every 15 seconds. That's what I run when I'm looking for performance data. I usually, on all my servers, run a 24-hour nmon that just runs all the time. It kicks off at 23:59 every day, and it takes snaps every 150 seconds. It takes 576 of them, and if you do the math, that's 24 hours. Okay, so let's look at UDP. Most people don't think about looking at UDP to see if there are problems, but there actually is something you should look at. And the first thing you have to look for is, do you have any bad checksums? If you have bad checksums, then you've got hardware or cable issues of some kind. You're also going to look for socket buffer overflows. Socket buffer overflows can be caused because you run out of CPU, because you run out of I/O bandwidth, or you may need more UDP transmit or receive sockets. Another thing to watch out for is if this is an NFS server, then check that you have enough NFS daemons. Those are all things that you would look at with UDP. Now, most of us are running NFS with TCP, but it is just something to be aware of. You're going to run your netstat-s or your netstat-p UDP, and you're going to look for, under IP, if you see in the fragments drop duper out of space, then you would increase your UDP send space. Under the UDP section, you're going to look for socket buffer overflows and increase your UDP receive space if necessary. Like I said, if you start out with it set to 10 times your UDP send, and if you use those settings that I gave you at the beginning, most likely you'll avoid these issues. And the next piece here is just talking about what I already talked about earlier, where UDP packets arrive in bursts, so typically 10x. TCP actually monitors buffer space. So if you exhaust the buffer space, you're going to get errors. UDP doesn't monitor the receiver. It just keeps sending stuff to it. So it's not going to stop sending just because the receiver runs out of buffers, and those packets will get dropped. I added a couple of slides in on network speed conversion because I wanted to make sure that people understood the differences. If you want to look at the differences between them, these are all the numbers here. And this is actually a spreadsheet you can get where you actually type in what your gigabits per second are, and it tells you what you get in gigabytes. Here I typed in one. I think I gave it 1 gigabit, and it gave me all the numbers, what it was in megs, what it was in bytes, etc., etc. 1 gigabit per second is actually an eighth of a gigabyte per second, so they pretty much divide by 8 to get the bytes. I actually find it useful because I'm more a bytes person than a bits person, but just be aware, big G, little b is bits, big G, big B is bytes. That's everything I have on the networking stuff for right now. In the next couple of slides, there are some useful links. These are the links for the articles that Charlie, Andy, and I have written. I've also got the direct links to Jay Krumke and Nigel's Twitter feeds. You don't actually have to be a Twitter member to look at them. You can just go to these URLs and look at their data. You're on a Forsythetalks right now, so I have the link here for the upcoming ones. Next month, we're going to actually talk about putting together a GPFS cluster. Additionally, I have a number of links here to Nigel's our expert blog where there are a number of postings actually on 10 gig networking, and obviously to the AIX wiki, HMC scanner, and so on. I want to thank you all for your time. Hopefully you found this to be useful, and if you do have any questions, please let me know, and you can email me and I'll get back to you. All right, thank you very much.